Hello, everyone. Come on in. I don't know what the heck's going on here. I accidentally pinned two people to my screen, did not mean to. Come on in, everyone. Nice to see you again. More of you in. My internet's being kind of wonky. Am I getting freezes or anything in the screen while I'm talking to you guys? Don't see any glitching or any of that kind of stuff.
The video is a little bit laggy. It says your network bandwidth is low.
Yeah, I thought I'd be able, I had 40-minute break between the last class and this class. I thought I'd be able to upload the video from last class in that time period, but that seems to not be the case because it says I have 41 minutes left uploading my video. I think I'm just going to kill it and do it again later. Maybe that'll help. Hopefully that'll help. Let's see if I can stop it. There it is. Give me an option to choose. So cancel upload. Okay, now I've got it canceling. Hopefully that'll stabilize it a bit. Thank you, Nina and Jordan. It should look a little better now, hopefully. It's finished taking the last video from the last class. It has to take that video and convert it to MPEG-4, and that takes up some processor time. Not internet time, luckily, because I'll load it locally, but the uploading to my YouTube channel does take some, so that was stealing some of our bandwidth. I'm going to go ahead and make up our document for today, PHY 242 D01 capital B, and then underscore 01182023. So you'll notice when you do the searches like that in your Google Docs, you'll find a document with that kind of name in it. And for instance, the Google Doc for today would be 01182023. So if you do a search in Google Docs, you'll find that doc by just doing a search for that. If you forget what day it is, whatever, it doesn't matter. If you're looking at a video on YouTube, what you'll see in my YouTube channel is in the comments, it'll have something about how you can reach me if you want documents. And then immediately after it, it'll have some mark like PHY 242. So you can see you can actually do those searches there as well. So just, hey, if you're looking for any lecture on 242, just do a search for PHY 242. And that'll pull them all up and that sort of thing. Giovanni says already let him. I don't know why. Oh, I wonder if he's using the one for lab instead of lectures. A different one for lectures than it is for lab. Can you let Giovanni know that? He might be clicking on the wrong one. All right, well, I guess I'll go ahead and get started. Hopefully Giovanni can get in. Why I couldn't get in now? Yeah, I don't have any reason for that, understanding for that. I have Zoom on the top left-hand side of my Canvas window. Do you guys have Zoom? I mean, I know you see it there, but what does it give you when you click on that?
It gives us links to join your Zooms.
It does.
Yeah.
So that one should be it. Let me check the password real quick. Maybe we can make sure it's that. He's got this. Sorry, everybody. I just don't like leaving anybody out. So looks like the passcode is this. So I got that part. John, can you send him this just to make sure? That should be the passcode for this one. Maybe if you cut some paste, so you won't make any errors, but sometimes you definitely get errors with it. So I would like to, I would ideally like to have a recitation, instead of meeting 3 hours a week. I like to do what we do at what I did at Chapel Hill and what we did at MIT, which was you offer 3 hours a week of mostly just conceptual stuff and occasionally solving a problem. And then you have recitation, which lasts a couple hours once per week, but it's completely optional. And then all students show up and grad students would, solve problems for you, stuff like that. I don't have another grad student, but I certainly have office hours and Zoom hours I can make for you guys if you wanted. But the real thing is, so chapter 21, I did the hardest and nastiest of chapter 21. I didn't do some of the other ones that were a bit easier than the infinite line charge, but I've spent enough time on it. And what I did was I went ahead and put some more links in our module for week 1 in Canvas to show you other types of examples you can do with Coulomb's law in integral form and with Coulomb's law not in integral form. So by all means, check that out. If you have any questions, if you're not getting it, make sure you contact me and we'll fix that up. I also put an extra credit in the bottom of, I think it's the bottom of week 1's module, but it says how far is too far or something like that. That is a chance for you to redo basically the same problem I did in class, that integral of an infinite line charge. But now instead of integrating from negative infinity to positive infinity, I'm just going to do the L over 2 from negative L over 2 to positive L over 2 and do some comprehensions. I know I explained that earlier, but just make sure you can do that. That's sort of the first step to making sure you can do these integral things. And the formula is pretty straightforward. I mean, it's dq over 4 pi epsilon naught. And then you take this vector RP minus, there he is, RP minus RDQ. You take the magnitude of that and cube it, that's in the bottom, and then you take it and just multiply it by the integral RP minus RDQ in parentheses, those vectors. So all you have to do the integral is, or to set up the integral is figure out a vector from your coordinate origin to the point at which you wish to know the magnetic field, or excuse me, the electric field. That's RP. And then you find a vector that points from the origin to your differential charge element, which is called R sub dq. And then you subtract them, take the magnitude, and just put the parts in and hope everything works out. So Giovanni finally got here. I'm happy now. Everybody's free to go on with our material. So again, that's what I'm saying about chapter 21. We've essentially finished it, but if you need more help, it's no big deal. I forgot to tell you this morning, but I plan on making everything that was due this past Sunday, or even if it was due last night, don't care, 11:59 p.m. or whatever. Everybody that got it done, even if they got a crappy score on it, but got it done by 11:59 on the due date that I was originally assigned, I'm giving you guys 100 and an extra credit assignment, and it's extra credit. So that means I'll increase the number of drops by 1, and everybody else will get zeros in it. So they're not punished. But the main thing is I'm giving you until Sunday, the 22nd, 11:59 p.m. to make sure you get chapter 1 finished, because I had those examples available to you on my YouTube channel, but looking at the attendance, I only had like 5 people go to them since Wednesday of last week. So that's not good enough. You guys aren't getting enough examples that way. So make sure you look over more examples. one thing that you need to be able to do, and ideally what you would do is you read the material before we cover it. So today we're covering chapter 22. Ideally, you would have already read chapter 22. Next time we're going to probably do a little bit more with 22, but we're jumping into 23. So you should have at least the first half of 23 read next time. If you look in our syllabus, it has that table that says what dates what are covering. So as you cover one chapter, just mark it out and you know the next thing in the list comes next. So you can always know what to read when we're covering it. Okay. With that being said, I'm going to introduce you to a concept of flux. I did it a little differently last night, but y'all can check that video out too. If you do a search for PHY242_01172023, that would be last night's 242 class. And I did a different introduction to flux. I'm going to do a different one. I think maybe hopefully works better. We'll see. And it's one I had experience with. I worked at Blackwater. I helped train some of the employees there in various things. And like they were working on the Grizzly and stuff like that. And I interacted with a lot of them. And there's some neat training that they do there. It's no longer called Blackwater, but it's literally right down the road from me. So I've done it for various classes. But one of the things they do, and this is obviously macabre and sad and stuff like that, but it's an interesting science to think if someone's trying to run you over and you happen to be armed, how do you do that? How do you take your gun and shoot in a way to try to disable the person from running you over? Because it's clear that a windshield is going to deflect a bullet, but how much is it going to deflect and in which direction? So I can use that idea of flux to discuss that, and I thought that might be neat. But let's stop for a second and remember, I'm not, this is a sad situation. You don't want to shoot anybody, but it is, from a physics standpoint, a fairly interesting problem. And we'll just try to take the emotionality out of it and the horrors of war and stuff out of it in general, and say it's sort of we're imagining a self-defense scenario, because there literally are. If you look on YouTube and TikTok and Instagram, you'll see all sorts of video cams, dash cams, where people are just coming to a stop at a narrowing of an intersection or like into a tunnel and just jumping out and trying to attack you in your car. So that's another scenario that we got to deal with nowadays. Luckily, that's mostly in third world countries, but it still happens. So it's not a good thing. So that's all I'll say about the political and emotional ramifications of shooting at cars. Obviously, I don't want anybody shooting at any living thing except maybe to provide food on your table or something like that. So, or maybe if you do it for sport, I'm okay to some extent with that, but that's neither here nor there. What I care doesn't really matter. So what I'm thinking about in flux is basically, you've probably heard the term in history before, but it's a different scenario when we talk about physics. What we want to know is how much of a certain thing can get through a certain area. So if you're thinking about bullets going through a window, you look like this. Let's say I'm going to take a bullet. Okay. And it's moving with some velocity v like this, and it's going to hit a windshield, which I'm trying to draw in some perspective right now like this. And what you know is going to happen is when this bullet hits the windshield, the bullet's going to feel like something tried to slow it down. Well, that force can be broken up into a component that's parallel to the windshield. In that sense, that the window is super, super strong. If you tried to take a windshield and set it up vertically, let's actually imagine a pane of glass, because windshields actually bend and it would make it look a little weaker. But to get an idea, the extreme situation would be a thick chunk of glass, let's say 3/4 or at least half an inch thick, and we stand it up vertically. And if you try to compress downward on that edge, and don't do this for God's sake, because when it breaks, it'll actually stab you and injure you badly. But the window is quite strong that way. You could actually put quite a large amount of weight on it. However, if you poked it perpendicular to the surface of the window, it wouldn't be very strong. So that's what I'm doing, is I'm breaking this response that the bullet feels, which is that blue vector coming off the window, is in fact made up of that red component parallel to the windshield, and then that other red component that is in fact perpendicular to the windshield. Now that one right there, parallel to the windshield, that's pretty much going to do all the deflecting, but the one perpendicular to the window is not going to do much. So in other words, you're not going to get much slowing down perpendicular to the window, just parallel to the window, you're going to get some slowing down. So that tells you if you're shooting into a windshield that's tilted like that, obviously the bullet's going to be deflected in a downward direction. Of course, the opposite is true if you're going to shoot out of one. So if someone's trying to hijack your car, maybe you're in South America or something where some of this bad stuff's happening at intersections or entrances to tunnels. It's really crazy. But yeah, you see a pretty well-developed infrastructure and then people jumping out of cars to hijack it. But anyways, if you had to shoot out, the same sort of thing goes on, but the same, you have to reconsider what would happen when you try to shoot out of a windshield, because your windshield's going to try to block it as well. So in this case, you expect the bullets to be deflected downward. So if you really wanted to, shoot on the upper body or something like that, you need to aim fairly close to the top of the windshield. Now, what does all this mean? Well, what this means is ideally, I would like to know what component of this is going to actually harm me. Well, it's the component that is perpendicular to the window that's going to harm me. And in fact, if I call this vector, this blue vector right here, if I call that the A vector, in other words, excuse me, not that vector, let's kill that. This vector right here, I'll call this A perp vector. Okay, so that little symbol for perpendicular. So what you want to know when you're actually, say, studying the ballistics of shooting into a windshield, you want to know how much the velocity component changed perpendicular to the window, because the one parallel to the window is going to actually change significantly, but you still got to see what kind of damage is going to happen to your bullet or so on and so forth by the windshield. So what really matters is how big of an angle does the velocity make with that little A perpendicular vector. That is a flux. And in fact, if you imagine instead of having a single bullet, let's imagine you have an array of built-in guns, not unlike you've seen some of the some of the cruise missiles, smaller versions of cruise missiles we have there. They're like a bank that's rectangular and it's got like 8 wide and four rows. If you imagine shooting that at quote unquote a rectangular opening that is tilted like this one, then that becomes irrelevant. So what you see, really what matters is you've got this velocity. Actually, I shouldn't do that color anyways because I did it the other way. What we have is this velocity vector that is this way. And then we have, in fact, this dA vector, or this A vector, excuse me, which is this way. And when you put these vectors tail to tail, you can see really all that matters is the component of the red vector parallel to the V vector. So this is our velocity vector. And this is our A perp vector. So the thing that's really going to bother the bullet is that component right there, which I can mark by this black part. Well, it doesn't even matter as far as the direction goes. You really just need what that magnitude is. And that magnitude happens to be A times, if you write these as their tail to tail, that would be the theta vector. And this would be cosine of 180 degrees minus theta. And that is exactly what that part is that little part right there, okay? You can look up your trig identities, but basically what you'll discover is that we can do this with the dot product. If I took the cosine of theta instead of cosine of 180 minus theta, then the cosine of this theta being larger than pi over 2 is going to actually get me a negative number. And that accounts for the fact that the A perpendicular is opposite direction of the velocity. So we can define a flux, if you will, and that's the symbol we'll use as a Greek phi. We can define the flux, and I'll say approximately because this is under very special circumstances. It's approximately V dot A perp. In other words, if you want to see what fraction of, let's say peas, let's say literally peas, like peas you eat. So let's imagine someone takes a bucket, several people take buckets of peas and they throw them towards your window, which hasn't been installed yet, by the way. It's just an opening in the wall, so there's no glass there, right? Now, having a big bucket of peas coming at you, okay, they're going to fly in the air and bounce up against each other and all sorts of stuff. And they'll be going every which way. You know, they're literally all these different directions of going. But really what you care about is the ones that make it through the window and make it so with a high speed. Well, the ones that are not going parallel to the window, they're going to bounce off all those other ones that aren't going parallel to the window. And they're going to bounce off some of the ones that are going parallel to the window. But really what you care about is that the ones that went from directly in front of the window and are traveling perpendicular to the window, in other words, going parallel with the sides of the window, say, so parallel to this or parallel to this side of the window, those are the ones that are most likely going to make it into the room that you're going to have to clean up afterwards. So that's another way of thinking about flux. So if you can find the component of velocities that are perpendicular to the hole, then you've got something that's meaningful. In other words, that number, if you divided that by the total mass, if you took the mass of all the peas inside and divided it by the total mass of all the peas, that would roughly be related to the dot product of the vector representing the window along with the velocity of the peas. Because you're just, by doing a dot products pick off parallel components, whereas cross products pick off perpendicular components. That's what you're going to learn, hopefully, if you didn't already know it from trig. So you can see another instance where flux would be useful. So this is the flux of a bullet going through a window. You could also have the flux of, say, peas going through a window, which is obviously a lot less traumatic and a lot less politically irrelevant. So probably should have been a better idea for me to do. But you could also say the flux of peas is about equal to the velocity of peas dotted with the A window vector. And we just define the window vector to be like, if you notice where the plywood or the siding of your house is, that defines a plane. The area would be the height times the width of that hole in that plane. And a nice, unique way to represent that area would be to create a vector whose magnitude is equal to the area of that rectangle, but whose direction is perpendicular to that plane. Now, you can obviously see if you're doing that sort of thing. Let me draw another example. Let's say you're looking at, let's go one more. You're looking at a window like that, right? Well, it turns out you can actually make an A vector that would be perpendicular to that. Okay, that's fine. But guess what? That's not the only one, because it turns out you could also do this vector. So it's somewhat arbitrary which direction you push this, what we call a normal vector. And normal is just the fancy word we learned last semester for perpendicular. It's the technical term. Well, it's the technical term for a vector being perpendicular to a surface. So there is some ambiguity. But when we go to use it for Gauss's law, which is what we're going to do in this chapter anyways, there's a way to actually handle that ambiguity. Specifically, in Gauss's law, we're only going to consider surfaces that are closed. So for instance, the surface of a cup would not work unless it was perhaps a two-sided cup. So this cup, for instance, it has a side and a bottom and a side that goes all around. But if you look right here, you can actually go inside the cup without crossing a surface. So that's not a closed surface. But if you realize this is a double-walled container, then you could say, okay, well, the walls of the container form an internal volume that's basically the air between the inner layer and the outer layer, and between the inner layer of the bottom and the outer layer of the bottom. That is a closed surface, because in order for you to go from what we consider inside to what we consider outside, you have to go through a surface. So that makes it an unambiguously closed surface. That's the kind of surfaces we have to deal with Gauss's law. We can't just take window panes and stuff like that. You've got to have it completely enclosed. Now, this method that I showed you, this dot product, is really wonderful. It allows us to pick off the components of the motion or the field or whatever it is you're talking about that are only perpendicular to the surface. If you had a sunlight for a skylight in your roof, for instance, the sunlight components that are perpendicular to that skylight plane are the ones that are going to make it all the way down to your floor, because usually the skylight is, let's say I'll draw a skylight. Actually, I have one in my house. It sort of looks like this on the roof. But then down inside, what you'll notice is it's got a long path that it goes through before it gets to my floor, or to my ceiling, that is. And because that path is that tunnel there, that rectangular tunnel is so long, any light rays that come in, let's say different than perpendicular, are going to be broken down into components that are perpendicular and components that are parallel. This black one right here, which is perpendicular to the surface, so that'd be light perp. That component is the one that'll make it all the way to the floor, because even if it's at the outer edge, it'll just skim across that little drywall tunnel. Whereas the other component, this one is actually L parallel to the plane. So I'm saying with respect to the plane now. This one, given the length of this tube from here to here, say, is highly likely to bounce off the walls and not make it to the floor. So that's yet another way Flux could make sense. And the way you do it is you define the arrow representing the actual sun skylight. You actually define that perpendicular to the skylight like that. So now if you take a dot product between that and this little vector, the blue one, you only get the component parallel to that, and that's exactly what we want. So everybody have some sense of what I'm talking about with that now? Y'all got an idea what Flux is? It just, Misner, Thorne, and Wheeler in gravitation, are what Austin people call MTW. They just say it's like every time a vector goes through perpendicular, it rings a little bell. But if it goes through parallel to the plane, it doesn't, it's not able to ring a bell. So that's another way of thinking about it physically. Now, the problem is these formulas that I just drew with a dot product between a vector and another vector, that works provided the area doesn't change direction over the whole area that you're doing. And two, that the vector, in this case, is the VPs or the A perpendicular, or the V, excuse me, if that doesn't change from one part of, say, the window to the other, then that's fine too. So you actually have to have the fact that the window would have to be a perfectly flat plane, or you'd have to go to such a small section that it is a small plane, a flat plane, and that can help you. The other question is, does the vector change from the bottom left corner of the window to the bottom right corner to the top right corner to the top left corner? If it has a varied magnitude or direction, I'll get you, John. If it has a varied magnitude or direction, then you're going to have to account for that at each individual part. So again, you might end up dividing the window up into little rectangles or little squares that are small enough that the surface is perfectly flat, and small enough that the vector thing that you're trying to calculate what's going through it, that vector thing doesn't change its magnitude or direction over that small rectangle. If one of them's not true, you keep making it smaller and smaller, and then you integrate it all to get the total result. Go ahead, John. What's your question?
So are you saying that flux, or like the physical like interpretation of flux, is like the rate at which something flows across a surface?
Yeah, that's a good way of thinking about it, because like if you talk about water going through a pipe, most of the water is just going to be going parallel to the pipe, and that's the stuff that matters. But some of it will be bouncing, perpendicular to the radius of the pipe, and that's not really contributing very well. In fact, it's just causing friction and stuff like that. So if you really wanted to make a device where the pipe works perfectly, you'd make some kind of, let's say, flux capacitor that could force the flux to become the only part that goes through there. So in other words, you might put a grid of wings across the circle or across the circular end cap, so it keeps everything only flowing parallel to the pipe. That would be a way of capacitating, if you will, the flux coming through the pipe. Does that make sense?
Yeah, thank you.
No problem. So this is a concept. It's somewhat important here because Gauss's law uses it, but it's super important when we get to electricity and magnetism. This flux is the very thing that makes us able to make transformers, and it's able to make your phone charge by laying it on its back on a charger without plugging anything in. That inductive process is due to a flux, and in that flux there's a changing magnetic field. And that changing magnetic field is creating a current, or the current in a loop of wire is creating a magnetic field that's changing. And then that magnetic field goes through another wire loop and it causes another flux. And then that flux is creating a changing current in the wire loop in the back of your phone and charging your phone. So that's what flux is. So if I actually had to deal with a more robust flux, in other words, one where the vector could change over space and where the surface is not 100% flat, then things get a little more dicey. So let's look at an example. So this might be a surface that we could imagine. And if you wanted to get a contour map, you could take slices, if you will, like this, just to see roughly what it's shaped like. Okay. And then you run slices like this to get an idea too. Something like that. Now you can see this surface is clearly not flat, right? So what you want to do is make a little area in it that's so small that it is flat. And then you're going to represent that with a little vector dA. It's a differential area element. So it might be, maybe it has a width of dx and a height of dy. So dA would be dx times dy. That would be the magnitude of it. Now, it might seem absurd for you to be thinking about a vector having a magnitude equal to the area of a rectangle, but does anyone know why that's not absurd? In fact, that's quite normal. Can anybody recall anything they learned? Specifically in trig portion of pre-calculus? Let me draw a picture to see if it jogs your memory. Do y'all know how to calculate the area of that parallelogram? Okay, so A cross B is what I was shooting for here. It turns out the cross product, A cross B, in magnitude at least, is equal to A times B times the sine of the angle between them when they're tail to tail. Now, if I imagine the projection of the A vector onto the B vector, what I'll see is this is the component of A. Parallel to B, and you can see that is clearly equal to A sine, excuse me, A sine theta. Oh, did I do it right? Oh yeah, sorry. That's clearly A sine theta. But this one over here, this is, oh, I wrote A sine theta. I meant to write A cosine theta. Stupid me. Let's fix that real quick. And I'll just leave that part off because that's not really the one that matters. But that's the component of E. I was erasing it. It turned my thing to blue. Okay, so that's the component of E that's parallel to B vector, which for some reason I wrote what looks like an R instead of a B. Okay, this is the component of A perpendicular to B, right? And in fact, that is given by A sine theta, right? And in fact, the parallelogram, if you know the length of B, which is what's listed right there is just B on the right-hand side of that equals, if you multiply that length, maybe it's 12 meters, times the length of A perpendicular, you get the actual area inside that parallelogram. So what that tells you is A cross B really does give you a vector 1 that's perpendicular to A, 2, it's also perpendicular to B, and 3, it's also equal in magnitude to the area of the parallelogram that was created by those two vectors. Okay, so yeah, that's a very common thing, is a cross product. One picks off components that are perpendicular to one another, i.e. A perpendicular to B. You could create another triangle and say you're picking off the component of B that's perpendicular to A, and it'd still be the same formula, but that's the main thing, okay? So you're imagining this dA, it might be gotten from an actual, this dA might be gotten from an actual cross product, and that's typical in differential forms and what some people offer as a third semester calculus. But the main thing is you see that there's clearly a precedent of people using the length of a vector to represent an area and people using the direction of the vector to represent a direction perpendicular to an area. So we've got this dA that's clearly perpendicular to the area. I've made a smaller area because it clearly tells me from those blue lines that I drew on there that that rectangle that it's in is not flat. It's got curves that tells me it's a curved surface. But if I made it small enough, it would be flat. And not only that, if I make it small enough, we can actually be lucky enough to only deal with vectors, because this is a vector field, to only deal with vectors that are uniform over the entire area. If the vector field looks like this, notice how it's changing at different locations. You know, in fact, it's not only changing direction, it's changing size and everything. So if you make that little rectangle small enough where you can see that the little E vectors, are all roughly constant, then all you have to do is take a dot dA and dot product it with E. So in fact, in this case, the flux, turn back to black. In this case, the flux, which is a differential area of flux, a differential element of flux, is just going to be equal to E dotted with dA. And that's our more general definition, because we have to allow for the fact that E is a vector field. And that means you take every little point in space relative to some coordinate, you'll have an X, a Y, and a Z for that particular point. And at that particular point, you assign it a vector whose units are newtons per coulomb, or later, as you'll see, volts per meter, and whose direction is also defined. and you tag that to that particular point, and then you go to another point and do that, and you have to do it with all the infinity of points in the space, and that's what electric field is. So our electric field can actually very much depend on X and Y and Z. That's one of the reasons we break down the area to a differential area element, so that we can take the limit of the dx or the dy or both of them as small as we need to, and we keep doing it over and over and over and getting smaller until we find that the e is small enough that when we multiply the e times the dA, we get the same result as when we do it with the next smaller one, or as we do it with the next smaller one still. So if you get 3 in a row, say, that are differentially, or excuse me, a factor of 10 smaller than the previous, and all 3 of them give you the same result, then you know that you've gone small enough in terms of the limiting process. That's the whole definition of a limit, is you're allowing things to get as small as they need to be so that they match your data to the appropriate number of data points. So if I was trying to calculate the flux to 4 decimal places, I would keep getting it smaller and smaller until E times dA gave me the same value in all 4 decimal places. And if I went the next layer down, it was still the same value in the 4 decimal places, but the 5th might be wrong, then that's still good as well. And if I go another one still, that'll still be good because it's still doing the 4 decimal places. Okay. So that's what flux is. And it's technically, when you go to compute it, it actually turns out to be this quantity right here, electric flux, not to be confused with electric boogaloo. Sorry, all my jokes spawned from the 80s. So electric flux is given the symbol phi. When we get into magnetism, we might subscript it E to remind us it's electric. But it turns out it's the integral of d phi, which is a scalar quantity, by the way. Remember, dot products are also called scalar products. So this is going to be equal to the integral of the electric field dotted with dA. That's what the electric flux is. This thing right here, this god-awful beast with vectors and dot products in it, is called a surface integral. And again, your calculus book will have it near the end. And if you were in a really a class where they had so many students that they already had calculus by the time they got there for the first day, they'd already finished, a whole year of calculus. And then you got to TCC and all those students were in the same class at TCC, then chances are by the 3rd semester, you'd actually get to cover stuff like one forms or vector calculus, surface integrals, line integrals, that sort of thing. But we usually can't. So that's why you often don't get it. But that's what that is, the surface integral. And what a surface integral means is you're computing an integral, and you got to make sure on each surface that you're doing, the integrand, which is E dot dA, has the specific values that are characteristic of that surface. So for instance, if your surface was a surface parallel to the XY plane and was up at a value of Z equals 4 meters, then you'd take your electric field, which is a function of X, Y, and Z, and you'd set all the Z's in it equal to 4 meters. And then you'd also realize, well, how far can I go in the X direction from what number to what number in the X direction, and from what number to what number in the Y direction to cover that whole surface? That's going to be put into the integral as well by making limits of integration. And the dA has to be perpendicular to that little area. And obviously that's got to be perpendicular. So that's going to depend also on the surface. So that's what we mean. The good news is the vast majority of times you can completely ignore the fact that it's a surface integral and avoid doing all the details just because you know exactly what the result will be. Okay, so let me show you an example of calculating electric flux. I'm going to take a very specific example that will be very instructional, if you will. So for our electric flux, I'm going to first draw a point charge. And I'll make that point charge be green, say. Okay, so there's a little point charge. I'm going to say this point charge has a charge Q. Now I'm going to put it in a coordinate system. And I'm going to try to make sure that point charge is dead center in the coordinate system. And I'm also going to make sure my coordinate system is in fact right-handed. So this is X, this is Y, and this is Z. And right-handed, remember, hold up your right hand, your index finger points in the direction of positive X, your Y, or your middle finger points in the direction of positive Y, and then your thumb should then point in the direction of positive Z. I think you can see this all does this when you just sort of point away from the screen. So this one's good to go. Now, what I'm going to do is I'm going to calculate the electric flux. So I'll say the question is, now I can't just ask you for the flux. I have to give you a surface through which the flux is going in order to make sense of this. So I'm going to draw a Gaussian surface, and it should in principle be centered on this this particular charge. And there it is. Okay. Now that's my Gaussian surface, if you will. I'm trying to realize that it's actually a sphere by drawing these other lines. Okay, so that's our Gaussian sphere. And in fact, I'll say that the radius of this Gaussian sphere is R. Okay. Now, here's where I'm going to make use of the idea that the vector dA has to be perpendicular to the surface, but it could be two ways. Well, when I made the sphere, the charge Q is inside of the sphere, and the charge Q cannot come outside of the sphere unless it goes to the surface. So that means it's clearly a closed surface. Because it's a closed surface, then I can make a rule about which direction the dA vector points. And the rule will be the dA vector always points outward away from the inside of the object. So we've got now a spherical surface, and what's going to happen is the dA vector is going to point radially outward. It will point radially outward because the center of the sphere is the origin, and if you connect any spot on the sphere with the origin, that line will be radial. Therefore, it will be perpendicular at that surface, and it'll be parallel to dA. So what I can now do is I can imagine a little patch of this surface area like this. And now I can imagine the little lines coming to it. Like such, okay? And this little vector right here, perpendicular, is going to be my dA vector. Now, those of you who are familiar with spherical coordinates, and I have an intro to that in my week 0 module. I do recommend you look at it. We're not going to use them in terms of you doing a lot of calculating, but we're going to use the symbols because they come in handy, and it's easier to just remember, hey, now that you know that this symbol means, I can draw that. Well, this dA clearly points from the center out, so it's what we call a radial vector. And in fact, if you had covered spherical coordinates, you would know that that little patch of surface area has a vertical side whose length is r times d phi, where phi is what we call the polar angle that's measured downward from the z-axis. That gives me that little arc on the left and right hand sides of this patch. And then the bottom and top side is actually given by r cosine theta, that being the radius of curvature, and then times d theta. So r cosine theta is the radius of curvature of that little bottom and top part. You just got to let theta, the what we call the azimuthal angle, staying in the xy plane. We've got to let that value vary from theta to theta plus d theta, and then you get that dA would actually equal r, because we had r d phi, and we also had r sine theta, so it'd be r squared sine theta d theta d phi, and then all of that would point in the r hat direction. Okay, remember, whenever we write a vector, a letter, and put a hat on top of it, that generally means it's a vector and its length is 1 unit, not 1 meter, not 1 Newton per Coulomb, just 1 unit. And that happens to be the one we represent by R. It points radial outward. That's the R unit vector, just like I, J, and K for the Cartesian coordinate system. Now that I did all that, you're never ever going to use that unless you've already had Calc 3. In fact, what we're going to consistently use is we're just going to call that dA R hat. Okay, so that's our differential area element. Now, what I know that at a given distance R, the electric field is Q over 4 pi epsilon naught times R, and that it too will point in the R hat direction, right? Because the charge is at the center, we assume it's positive, because if you replace it with a negative number, then you'd actually multiply that charge times a -1, and that would force the vector to point the opposite way, so it self-correct. So we know that the electric field actually points radially outward, so that is our electric field, okay? And you see that they happen to be parallel, and that's wonderful, because that's the way we're going to use Gauss's law. Is we're going to only choose symmetries such that the R is always, or excuse me, the electric field is always either parallel to the dA vector or perpendicular to the dA vector. Okay, so now that we have that, I can say the flux electric is equal to the integral of E dot dA. And that, of course, becomes the integral of Q over 4 pi epsilon naught R squared. Oops, that's supposed to be R squared down there. I forgot to square it. Everybody make that correction. That multiplied by R hat. And then I'm going to dot dA R hat with it. Now, this dot product is linear. What does that mean? Well, linear means if you take the dot product of a number times a vector, it's the same thing as multiplying the number times the dot product between the two vectors. So if you had A times, or A dot CB, where C is a constant, that's the exact same thing as saying C times A dot B. Similarly, if you had, let me quickly write this down. I'll do it this way in a different color so we can get something nice out of it. I'll do this pretty little pink color. Okay, if I did A dotted with C B plus D C like that, the fact that it's linear means that I can have C A dot B plus D A dot D, or D dot A. No, A dot C. So that's what linear means. It means you can just pull all that crap in front if you really wanted to. Okay. So with that in mind, that means I can pull the dA over here. Okay. So I'm going to go back to my blue and get off that god-awful pink color that looked like foundation color. Ugh, I hate the color. I don't know why, but I just do. Okay. So now the flux, the electric flux continues. In this case, I can now see that, notice the Q is a constant. And since we're actually on, remember this is a surface integral, so we're integrating on a surface. The surface happens to be that sphere of radius big R, right? So I can actually evaluate that. That little r has to be big R for starters. And because of that, it's all a constant. So I can pull it out in front, and I'm going to have Q over 4 pi epsilon naught big R squared, all that in front of the integral, times dA R hat dot R hat. Okay. Don't forget, A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So what do you think R hat dot R hat is?
R squared cosine theta.
Very close, but you're forgetting the little hat. Okay. Well, you're forgetting the little hat, and then you're forgetting that the two vectors are the same. But yeah, you're reading it exactly right. Know what's going on here. But remember, R is the length of a vector R, but this vector is R hat, so its length is 1. And the other length is also 1. And then in addition to that, you have to take the cosine of the angle between them. But what's the angle between two identical vectors?
0.
Yep. So you get 1 times 1 times the cosine of 0 just gives us 1.
Wait, so you're saying that r hat times r hat is 1 times 1 because r hat is a unit vector? Just to
Exactly.
Okay, thank you.
Yep. Yeah, that's why it became the 1. And both of them are the same, so that's why both of them are 1, and they're the same vector, so the angle between them has to be 0. So the fundamental theorem of calculus says that the integral of dx is just ignoring constants that you add. What would be the integral of dx? Wouldn't it just be x? So in the same vein here, we're integrating dA, where dA is a surface area element, but we're doing it over an entire spherical surface. So the surface area should be what the integral of dA is, and the area for a spherical surface is 4 pi r squared. So I'm going to write Q over 4 pi epsilon naught r squared times the integral of dA is a, and that's just 4 pi r squared. Okay. Now you can see what happens. This 4 pi cancels out with this 4 pi, and this r squared cancels out with this r squared, and we're left with nothing else but Q over epsilon naught. Now notice this is actually the charge enclosed. So when you do this with Gauss's law, when you do this with the electric flux, you discover Gauss's law. And this was done for a very specific case, but it turns out it's right in all cases. So now we can say Gauss's law says the electric flux over any closed surface. So that's why I put that. Notice I got an integral with a circle over it. That's a fancy mathematical symbol that we can use to remind you, hey, this surface integral is 1, a surface integral, but 2, it can only be done over a closed surface. We'll use that circle again later when we do a line integral, but again, it has to be done over a closed loop of wire in that case. So the electric flux, which is the integral of the electric field dotted with the differential area element, is equal to Q enclosed over epsilon naught. That's Gauss's law. And in fact, it's a weird law. It's what we call an integral equation, but it's an integral equation, which is something you've probably never solved. Now, it is Gauss's law. It's not Gauss's handy dandy trick that sometimes works. It's Gauss's law, so it's always true. The problem is what we're going to do with this in this chapter and the next 2 or 3 chapters is we're going to use it to solve for E. So we're actually using it to solve for the integrand. That's a weird thing. And this is not your typical formula where you say, okay, there's a symbol on the left-hand side, and then it equals some formula on the right-hand side. So you write down the symbol, you write down equals, you write down the formula, then you hit equals and you put in the values, and ultimately it works out to a number. No, you can't do this way because we're solving for E. What we have to do, and this is the way I've chosen to do it, is we have to evaluate one side at a time. Let's say this side shall be called the left-hand side, and then this side shall be called the right-hand side, and I'll work them out and then set them equal to each other and then solve for E, and that allows me to use Gauss's law. So the problem is you can only do this kind of trick with this integral equation under very specific symmetries. The symmetry has to be one that the closed surface has a differential area element dA that is either parallel to the electric field, in which case the electric field's a constant on the surface, or the dA is perpendicular to the electric field, and in which case the flux is 0 for it. Okay, by doing that, you're always going to get a really simple answer on the left-hand side. You're going to get either 0, or you're going to get E times A plus E times A plus E times A for however many surfaces there are. But that's consistently what you're going to get. Your left-hand side, y'all might want to write this down. I'm not putting it on here, but your left-hand side of Gauss's law used this way is always going to reduce either to 0 or E times A plus E times A plus E times A dot, dot, dot for however many surfaces there are. So let's show you an example. Okay. A non-conducting sphere of radius R is charged uniformly throughout and its net charge is Q. What is its electric field for R less than big R? That'll be part A. And part B for R greater than big R. Okay, so that's a typical Gauss's law problem. We got about 15 minutes. We should be able to knock this out. Let's do solution. Now, because this is a uniformly charged sphere, that means any volume, let's say we cut out a 1 millimeter by 1 millimeter by 1 millimeter chunk of it, and we measure the charge on it. If you take that charge and divide it by the volume in cubic millimeters, that'd be 1, obviously, you get a number, and that number is called the charge density and is given the symbol rho. Okay, so another way of saying that is rho is defined to be dq over dv, and since it's uniformly charged, that means if I went anywhere else and chose a single millimeter by millimeter by millimeter, we'd get exactly the same charge. Not only that, if I went somewhere else and took a centimeter by centimeter by centimeter chunk and measured that charge, if I then divided that charge by the volume and then made sure I converted the units to coulombs per cubic millimeter, I would still get the same answer. So that's the key to understanding uniformly charged. Not only that, when I consider inside of the sphere, we're going to have a smaller amount of charge applicable to us because all the charge further out than us will sort of cancel out the electric fields acting on us as a result of them. And we'll see that in a second in Gauss's law. So let me start off by drawing our neat little sphere of charge. So our spherical charge is about like that. I'm going to make our coordinate system like that, and like that. And what I'm going to do now is remember this radius right here is capital R. I'm going to take it off of that. I've got that. Now what I'm going to do is I'm going to consider part A, which is R less than big R. And I'm going to create what we call a Gaussian surface. Trying to make this a little better centered, but I don't know what's going on. That's pretty good. Okay, I'm going to make a Gaussian surface, and a Gaussian surface can be any shape you want, but it's got to be a closed surface. And ideally, you want to be able to do it such that the electric field is perpendicular, or excuse me, is parallel to dA everywhere or perpendicular. So I'm going to draw another sphere. Actually, I'm going to try to make it an actual sphere, so I'm going to cheat. Okay. And that's supposed to be a concentric sphere with the last one, but it's not letting me pick that one. There you go. Okay, it's not letting me move it, but the main thing is it's supposed to be concentric. That's sort of close, but not really. Why is it making it bigger instead of moving it? There you go. Okay, now it's pretty good. Okay, the radius of that sphere, on the other hand, is just little r. Okay, but that's our Gaussian surface, and it has one of those little patches on it like the one I drew in the last thing, but I'm going to make a hypothesis. Thanks a lot. Autocorrect, stupid head. So my hypothesis is because of the spherical symmetry of that mass of charge inside the Gaussian surface, because of that being spherical, I think the electric field in there is going to be given by the electric field is only a function of R. Spherical symmetry means it only depends on how far away it is from the center, and that it's going to point in the radial direction. So I'll put an R hat on it. My dA, of course, is going to be dA is equal to dA R hat, like that. And I don't know why I wrote it in red, but it's in red, so we're going to stick with it. So now I'm going to write out the left-hand side. Remember, I showed that earlier. Left-hand side just means the left-hand side of Gauss's law, which is the closed integral of E dot dA. Now, the point is the electric field is always going to point radial outward, and the dA is always going to point radially outward, so we can get some really nice cancellations. Not only that, we're doing, remember, a surface integral on that red spherical surface. So what we get is the integral of E of R hat dotted with dA R hat. Again, the linearity of the dot product operation allows me to pull the dA to the left of the other R hat. And the fact that we're on a surface means we're at a fixed distance R, so that E of R has to be constant because E only depends on R. So I can actually pull the E of R out in front. So I get E of R times the integral of dA, or excuse me, no vector on that one. I've already gotten rid of the vectorness of it, times R hat dot R hat. And anybody want to remind me what R hat dot R hat is?
2.
In this case, remember, it's the magnitude of R hat times the magnitude of R hat. That's 1 times 1 times the cosine of the angle between them. So it should be 1, right? Same thing we did there, remember? Oh, where's it at? Oh, yeah. There it is. Everybody see it? Get rid of that. Okay. So now what we get is E of R times the integral of dA. That's just like we did before. And remember, that was the rule I told you. The left-hand side of Gauss's law is always going to become some E times A, or multiple E times A's, or 0. So in this case, we're going to get just E of R times 4 pi R squared. Now the right-hand side, and this one's a little more complicated. It's just Q enclosed over epsilon naught. Now, the way you calculate charge, by the way, technically should be something like Q is equal to the integral of rho dV, or it's equal to the integral of sigma dA if it's a surface charge, or it's equal to the integral of lambda dL if it's a line charge. And of course, the rho is like we're dealing with here. It's a uniform density charge. So we could actually do that integral with that. It's not a big deal. And in fact, it's not that hard because the rho, as we said right here, rho is a constant. And in fact, I know for a fact that rho should be equal to Q over 4 pi R 4 pi R cubed, because it's charge per unit volume, and volume is 4/3 pi R cubed. So the 3 comes on the top. I know for a fact that is rho. Okay, that's just the definition of uniform charge. So in this case, I got to calculate Q enclosed. And since I'm not taking up the whole sphere, it's clear that Q enclosed has got to be smaller than the total Q. But the fact that rho is a constant allows me a way. So I'm going to say rho equals constant implies I've got 3Q over 4 pi R squared is equal to Q enclosed over 4 pi little r, little r cubed. Okay. And actually, I should probably make that a little better. Okay. So from that, I think you can see that Q enclosed is going to be equal to basically R cubed over R cubed times Q. Okay. So that's the easy way, just using the ratio. And as long as it's uniformly charged or uniformly distributed charge, you can always just set rho equal to rho. Okay. If it's uniformly charged over a surface area, you can set sigma equal to sigma. Sigma, of course, would be charge divided by the area, and lambda would be charge divided by the length. So in this case, I'm just going to say the answer to the right-hand side is 1 over epsilon naught times R cubed over big R cubed times Q. Now I'm going to set left-hand side equal to right-hand side of Gauss's law. And that's going to give me E of R times 4 pi R squared is equal to R cubed times Q over R, big R cubed. Okay. Which I think you can see, given my original hypothesis, the electric field must be equal to Q times R over 4 pi epsilon naught R cubed, pointing in the R hat direction. And this is for R less than big R. That's it. So notice again, the left-hand side is always going to turn into a E times A, or maybe it'll turn into E times A plus E times A, or maybe it'll turn into 0 plus E times A. That's the key point. Now, the other part, B, is actually a lot easier than this. So B is for R greater than big R. What we do then is we draw another sphere, another Gaussian sphere, like that. But I think you can see that the left-hand side is still going to be E of R times 4 pi R squared. And the right-hand side is going to be even easier. It's going to be Q over epsilon naught, because the total charge inside is just big Q. You don't have to do any computing with it. So we're done with that. So if I set the left-hand side equal to the right-hand side, I get E is equal to, I'm going ahead and applying my hypothesis. E is going to be equal to big Q over 4 pi epsilon naught R squared in the R hat direction. And this is for R. And you can notice now, if I plug in big R in this expression for little r and do the same thing in the other expression, you'll see that they're actually equal. So I'm going to say, instead of greater than, I'm going to say greater than or equal to, and say the same thing over there. So now I have the entire answer for this electric field. So it turns out this electric field is linear from R equals 0 to big R, and then it falls off like 1 over R squared. Let me quickly draw that graph for you guys. So right here is going to be Q over 4 pi epsilon naught R squared. Right here is going to be R. So put a dot right there. That's what the graph of the electric field magnitude looks like. Okay, now we only got 1 minute left. I wanted to do another example for you. I'm definitely going to do another example next time, but I would like you to look on to my, let's stop sharing for a second. I would like you to look on my YouTube channel. And let's say that would probably be, boom, that'd be this one. Okay, on my YouTube channel, let me turn it up now. Oh, it disappeared. Oh, there it is. Okay, so it's this one right here, electric flux, Gauss's law, and 2 examples. So the last couple minutes is me working out another example. In that case, it was an infinitely large plane, but it's in there. So you can go ahead and look at that as well. But you can also just look at any of my videos regarding Gauss's law, or in my YouTube channel regarding Gauss's law. So all you have to do is don't search up here, search down here, and just do Gauss. So Gauss's law, a non-conducting, non-uniformly charged sphere. Here's one where I souped it up and I made, instead of rho being a constant, I made rho a function of R. Here's one where I'm actually calculating capacitance, but before I can calculate capacitance, I got to use Gauss's law. So the first part of the very first problem is another instance. Here's another instance of Gauss's law. No, that's the actual one I just did. Here's an older video I did 11 months ago. Here's another one using Gauss's law initially, but then I'm ultimately going to go into next chapter. So you can find a lot of different ones in here with Gauss's law. Basically, the deal is, when you're doing Gauss's law in the way that that I just taught you, which is solving an integral equation for the integrand, it needs to be either infinite plane symmetry, infinitely long cylindrical symmetry, or spherical symmetry. If it's not one of those 3 symmetries, then you're not going to be able to extricate that E electric field out of the integrand to get it to work. It's still true. Gauss's law is still true. It's just not going to work that way. You can use the left-hand side to find out the charge if you wanted to, or you can use the right-hand side to figure out the flux if you want to. But the other part's not. So you guys are free to go. I will wait for the last person to go in case you have any questions. But thanks for coming, everybody. And this video will be posted sometime tonight, I suspect.
I just had a quick question about the lab that's due today. On Canvas, it said the deadline for it is midnight tonight, but it was already graded.
Yes. Just post it anyways, and you'll still get credit.
Okay, awesome.
So
Thank you.
by the way, all labs are always due before class on the next lab day. So for future reference, I know I did set it differently for this
Okay.
one just to give you all a break, but for all the rest of them, you wanted to make sure you turn it in before lab, which is 9 a.m. on Wednesday. Okay.
Okay, awesome. Thank
No
you.
problem. See you, Nina. John Wells, when we do surface line integrals in this class, are we going to have to worry about the orientation of the surface? Yes. In fact, you'll see in one of my YouTube videos on Flux, you'll see me actually compute a surface integral over a rectangular solid. So it'll have a horizontal top, a horizontal bottom down here, vertical left side, right side, the vertical front side and back side. In that case, you automatically are going to say, well, my dA vector for this top surface is positive k hat times dA. And you're normally going to do a single integral. So you'll say the width of it times dy if you're integrating in y, or you'll say the width of it times dx if you're integrating in dx. And then the bottom surface will have a negative k hat times the dA. And the right surface will have a positive I hat, and the left surface will have a negative I hat. And the front surface would have a positive j hat, and the back surface would have a negative j hat.
Great, thanks. So my computer froze in the
I
middle,
saw you
so I
lost. Yeah, I
didn't.
saw you disappeared.
Yeah, oh, it was bad. Like I just had to like hold the power button for like 30 seconds for it to like shut off. But I didn't get the rest of what you wrote down for when you set the left-hand side equal to the right-hand side.
Okay. Let me show it to you real quick. And remember, this video will be posted, so you'll actually get the best part of the video that you missed. But that's what I have.
You posted on YouTube?
Yeah, it'll be posted on YouTube tonight, probably at the latest. So let me pull up the screen.
Okay, great.
And the
I'll
notes
just
will be posted there as well.
Thank you.
Or not there, they'll be posted in my Google Docs. So you can see down there, was it this part when I was solving Gauss's law, or I guess it had to be this one because I didn't start doing left-hand side equals right-hand side stuff. So you can see down there.
Yeah, it was that.
Yeah.
Yeah, I got it now. Okay, thank you.
That makes sense?
Yep.
All right. Any other questions?
I think that's it.
All right. Sounds good, man. Well, you have a good one, John, and I will see you Monday.
Okay, see you then.
Bye-bye.
Bye.